Let us begin our discussion on orbits by properly defining them and what we mean by satellites. So, starting with orbits is just a description of how one body is falling around the other. And this is going to be a recurring theme when we discuss about orbits. It's all about falling towards the other thing. It's not about rotating around it. It's part of the picture, but all of it's captured with the idea of falling. And another thing we'll describe is that satellites, in terms of astronomy, we don't think of satellites as being something that humans have launched into orbit and put around the planet. No, satellites is a broad term. It just refers to one object orbiting another. And we always say the satellite is the less massive object. So an example on the text here, we'd say the moon is a satellite of Earth. We'd say Earth is a satellite of the sun. Right? That's what I mean by satellite. It's the less massive object who is gravitationally bounded to the bigger one and orbiting it. So imagine we start off with two objects, blue and red, that are in orbit around each other. Well, what they're going to do is orbit around their common center of mass. Let's go ahead and animate this. Right? So the black dot represents the center of mass between these two equally massive bodies, and they're doing a nice perfect circle around that center of mass. Now let's go ahead and upgrade, complicate the problem. Let's say one object is more massive than the other. So for example here, we'll say that they're still going to orbit the same center of mass. Here's the sun, and we'll have Jupiter be the less massive object. So we point out here, well, the sun has a center of mass, but due to how massive Jupiter is, the center of mass between sun and Jupiter is going to be slightly off a bit. Right? So the center of mass will not be right smack dab in the middle between the two objects. It's going to be bias, pushed towards the heavier object. Now let's go ahead and pull up the animation of the two objects. So here in our example here, this will be the sun, the more massive object, and this will be Jupiter. And the center of mass has been shifted away, closer towards the sun. All right. So, some things to notice here. The sun is going to have a much smaller radius away from the center of mass. Correspondingly, Jupiter is traveling a much greater distance, traveling a lot further. Now keep thinking of this orbit of the sun and Jupiter and ask yourself, which one's moving faster? Is it the more massive object, the less massive, or do they have to move at the same speed? Now go ahead and pull up the animation again. All right, you can watch that and now try and convince yourselves. Go ahead and pause the video and come back when you're ready to analyze it. So, let's discuss this in detail. Yes, it is going to be the less massive object who is moving faster. And here's the rationale, right? The speed of an object goes as the distance divided by the time. So if I label speed just the v, or like velocity, how far are they traveling? What's the distance? Well, they're covering a given circumference. Now, which one has a bigger circumference? The less massive or the more massive planet? Blue, the less massive one, has a much bigger circumference. Now, as for their periods, the period would be their time of flight, the time they're orbiting around that common center of mass. And watch the animation. See where they start. We'll go from the beginning. Start the timer. All right. Keeps going, and stop. They are orbiting with the exact same periods. So, if they have the same periods, the only thing different in their speeds will be their circumferences. The less massive object is traveling a greater distance, so that one has to be moving faster. So you want to get something in orbit. How do you do this? Well, we'll describe what Newton, he was the first one to come up with this, so he called it Newton's cannon. And here's the concept. Take a cannonball and you shoot it. Right? No matter how fast you get that thing going, it's always going to have g, little g, pulling it back down towards the surface. So you'll fire off with some tangential velocity, and it'll plummet into splash. It hits the ground. So, put more TNT, more explosive. Get that ball going faster. It'll have a greater tangential velocity. It will skim the surface skin until it crashes down, hits the planet. All right, keep going faster. As long as you can keep going fast enough. Go a lot faster. You're going to get a greater distance before gravity causes you to crash down. So, logically, if you go fast enough, right? If you have a critical speed, if you're going fast enough, then as you are falling towards the planet, you're moving so fast that you never hit. You're always falling, always in perpetual free fall towards the planet. There is a gravitational force constantly dragging you down. But because of how quickly you are moving to a position where you don't hit the planet. Now, if you slow down even just a little bit, just a tiny amount, then you're going to eventually crash down to the surface of the planet. If you speed up, well, now you're going to take this circular orbit and you're going to stretch it into an ellipse. Just pull it apart. So, gravity is providing a centripetal force. Think about the ball in a string going around in circles, right? When the ball is going in a string, the tension in the string is keeping that ball going in a circle. Well, when you're a satellite in orbit around a planet, the tension in the string is gravity pulling you down, providing this centripetal direction, the centripetal force. So, things to clarify, you are always accelerating, you are always falling towards the planet. There is a constant force on you. You just happen to be moving fast enough to not hit the planet. And the shape of your orbit, here you're doing a nice perfect circle. Well, once again, speed up, you're going to stretch that out. And we'll get to this concept of what kind of orbit you have depending on the speed that you're moving at. So imagine you were an astronaut in space. What's happening to you? Well, you were moved, you were accelerated and launched such that you had that critical speed so that you were always in free fall. And what about the space shuttle that you're in? Well, space shuttle, same problem. Space shuttle is going that way with enough velocity so that it can't crash down to the planets. Now both you and the shuttle experience the same acceleration towards Earth. So here's the trick. You are in this free fall with the shuttle and you feel like you are weightless. You still have mass. There are still forces on you. Hey, if there is an acceleration, there's a force on you. But you get this sensation of weightlessness because the environment you're in is moving with you. That's why you always see astronauts doing like those games of flipping around or squeezing droplets of water and drinking it with a straw. The drops, the liquid, the astronaut in the space station, they're all falling at the exact same rate. Think of it as like terminal velocity if there's any skydivers out there listening. Right? Because everyone's moving at the same rate, having the same accelerations, you get this odd sensation of zero gravity. Now, for those of you who are not fortunate enough to be astronauts, you still can experience this. You can go on what's called a reduced gravity aircraft. And I love this picture. There's a picture of Stephen Hawking from, I believe, back in 2007. He got an opportunity to go on this. So the way these aircrafts work, you get yourself high enough into the sky, about 24,000 feet. And then you would just go on this like ballistic trajectory. You would tip the nose of the airplane high, like at 45 degrees. Thrust. And then around here, cut the engines. You don't actually kill them, you need to keep them on, but you would stop your thrust. And from this point on, throughout this part, you're basically a ballistic, a giant projectile. Imagine an ant was riding a tennis ball when you lobbed it over to your friend. And at the peak of that motion, the ant and the tennis ball are going to be falling at the same rate. So, when the aircraft is going through this ballistic trajectory, the passengers inside the craft and the craft itself are all falling at the same rate. And so you get this wonderful free fall, this weightlessness sensation. Now, it's only good for about 30 to 40 seconds. So after that, what the plane will do is take over again, start catching drag, and stabilize itself. And then you repeat. You keep going up and down. And these are a wonderful thing. If you ever have the finances to afford a trip or get involved with scientific projects, I definitely suggest looking into this kind of experience. The way it goes is that they'll do several of these parabolic flights and do a sequence of these about 30 seconds free fall activities. For scientific discoveries or investigations, before you send a satellite into space, you want to make sure that thing's working correctly. So you'll have accelerometers on your device, and you want to make sure that it is detecting its orientation correctly while it's in free fall, so you can get a chance to fly on one of these if you do any sort of experiments that involve putting a satellite in space. Or if you got, I believe it's like 20 grand the last time I looked at the values, you can just buy yourself a commercial ticket on these things. Now, one last comment before we move on from this. These flights, they're technically called these reduced gravity aircrafts. They also have the fun name of a vomit comet. I'll let you wonder why they call those that. As I said before, there is a critical speed in order to get an object moving in a circular orbit around a planet. And finally, we have it. Here is that critical speed to get yourself moving. We say it's V circular is equal to the square root of gravitational constant, the mass of the planet you're orbiting, and the distance from the center of that planet that you're orbiting at. So this is true for any object that you want to put in orbit around it. This is the critical speed to do a nice circular orbit. And this was found by applying Newton's law of gravity and the second law. Now, I'm not showing you the details. That can be in supplemental materials. But let's look at a consequence of this law. The period of orbits, the time it takes to go once around the planet, is the ratio of the circumference of your orbit divided by your circular velocity. Well, we know what these expressions are, right? The circumference is 2 pi r divided by your circular velocity, square root gm over r. Now I'm going to rewrite this equation. I'm going to square it, do a little bit of algebra, and I'll tell you the result, right? Square both sides, and I'll end up with this p squared is equal to 4 pi squared r cubed divided by universal gravitational constant times the mass. All right, thinking caps on. This formula that we just found, we found this by applying Newton's laws. What is this thing? All right. Pause the video, come back. So what is this thing? Well, let's highlight the constants, right? 4 pi squared gravitational constant and the mass you're orbiting. These are all the same thing, right? They're not going to change. Well, I see a p squared, a period squared, and a cubed radius. That's Kepler's third law. The orbital period squared, the sidereal period squared, has to be proportional to the cubed radius. Well, here's that proportionality constant now. And this is a wonderful, amazing result. What Kepler found empirically, he said, look, I look at the data of planets orbiting around the sun, and there is this relationship. That squared period relates to the cubed radius, how far away the planets are from the sun. Newton, using his laws, no data here, just using his laws of gravity and the second law, he's able to say definitively, hey, that constant is this thing. What is proportionality? Well, it's this. So this is an amazing result. And some things to think about in the future. Look at this. Can we measure the period, the sidereal period of the planet? Yes. Can we get the distance of the planet? Copernicus got both of those. Well, if you have the universal gravitational constant, you can find the mass of the planet. So as a recap, Newton was able to derive all of Kepler's laws using the law of gravity and his laws of motions, his three laws of motions. Newton could explain all three of Kepler's laws using his physical models on the universe. And so when people were testing Newton, back when he first published his works in the Principia, people were testing in comparison with Kepler's laws. How well was Newton replicating what Kepler had initially stated? And Newton's law stood the test of time, and that's why we hail him today as one of the greatest scientific minds out there. Let's go ahead and start looking at the type of orbits, the shapes of what you're going to do. So if you're moving at the critical circular speed, then you'll have what's clearly a circular orbit around the planet. So how do you change that? How do you go to elliptical orbits? Well, you start moving faster. If you speed up, then you're going to have this elliptical shape. Now I'm going to take this and I'm going to tilt it on its side to once again re-emphasize this concept of this falling towards the planet. So in this picture, you're looking at the satellite. It's at its peak velocity when it's closest to the planet. And that's akin to a person throwing the ball, right? When you let go of the ball, it has its greatest speed at that moment. Now as it goes through its orbit, the satellite will go up and it slows down. Gravity is pulling it down, causing acceleration, slowing it down. It'll reach a peak. At this peak, it's moving the slowest it can go. And then it'll continue falling back down towards the planet. Now, the ball in this example will eventually hit the surface of the planet and just crash down. But the satellite, the space station in this diagram, it gets to keep falling and repeat. It slingshots around, gets a gravitational boost, speeds up, and whips around again. We give these types of orbits geometric names, and that comes from this cone here. Well, you have a circular, elliptical, parabolic, or hyperbola type of orbit. So, if your speed is the circular speed, then obviously you're going to have a circular orbit around the object. Speed up, and you go from a circular to an elliptical one. And you can speed up again. Keep going a little bit faster, and it will just stretch out the ellipse. The faster you move, the more you stretch the circle into a more and more elongated ellipse. But watch the pattern. If you keep stretching the ellipse, eventually you're going to break. You're going to break free. In other words, you are going to escape. So, these guys here, we would call these bounded orbits. You are orbiting around the planet and you are bound to it. You are bound to that object. But if you go too fast, if you reach a escape speed, well, now it's unbounded. You have escaped the gravitational pull. You are moving fast enough, you have enough energy to escape the gravitational pull of the object and fly free. So these type of unbounded orbits geometrically, this example here would be called a parabola. You could go to even more extreme speeds, have a velocity greater than the escape speed, and this would be called a hyperbola. The naming conventions comes from geometry. What matters for you, the student listening to this right now, is that this here are our bound orbits when you're between the circular orbit speed and the escape speed. If you're at the escape speed or faster, then that will be your unbounded orbits. You are escaping the planet. So as a reminder, the planets move in elliptical orbits. If you move at the circular speed, square root gm over r, there's your circular orbit. Speed up, you get to go into ellipse, go faster, and you get to escape away from the planets. So these consequences, once again, agree with Kepler's law. And at any point along the orbit, gravity is changing your speed, constantly trying to get you to fall back towards the planet. Except for the instances where you escape. While you're along this orbit, the gravity's still acting, pulling you in, but you're going so fast that it's just not enough gravitational pull to trap you anymore. So you'll get your trajectory altered by going near the planet, and then you will keep zooming off through the cosmos. A natural follow-up question is, if we know the circular speed, do we know the escape speed? Well, the answer is yes. And once again, we're going to gloss over the details. I'll just give you the result and say the speed that you have to go in order to escape the gravitational pull of the planet will be square root 2 gm over r. Or, rewriting this, it's square root 2 times faster than the circular orbit speed. Now that root 2, that comes from talking about energy considerations. You have to say there is a certain amount of energy that's keeping me bounded to this planet at this radius. Good point to emphasize here. This r does not refer to the radius of the planet. This r refers to the distance between you, the object orbiting, and the center of that planet. All right? So, when you want to calculate how much energy you need to escape, there comes this square root 2 factor. And that square root 2 just means that that's the amount of energy it takes to be moving fast enough to get over the gravitational pull of the planet. So as like a sample calculation, if you were to say have the strength of Superman, how hard would you have to jump? How fast would you need to be moving if you were right here on the surface of the planet and you needed to move fast enough to escape? Say you wanted to jump towards the moon or something like that. Well, that'd be 2 times gravitational constant, 6.67, 10 to the minus 11th, newtons meters squared per kilogram squared. The mass of Earth. Here's the mass of Earth, 5.97, 10 to the 24th kilograms. Now the radius. In this example, that's you on the surface of the planet jumping up. So the radius will be the radius of just Earth, 6.37, 10 to the 6 meters. And so it turns out, if you wanted to get yourself out, away from this planet, you need to be moving almost instantaneously at 40,300 kilometers an hour. One last crazy one that I love to talk about when in terms of orbits comes from a 3-body problem. So if you have a 2-body problem, think of the moon and Earth. Right? There's 2 bodies. What are all the types of orbits they can have around each other? But remember, you have the moon orbiting the Earth, which is orbiting the sun. So there are 3 bodies involved. And you have the tug of the sun on the Earth. You have the tug of the sun on the moon. And you have the tug of the Earth on the moon. And you have the tug of the moon on the sun. And so forth. So you get this crazy 3-body interactions. All right, so what are the orbits going to look like in this crazy problem? And there are an insane number. But we're going to talk about one special type, and that's called the Lagrangian points, or also known as the Lagrangian equilibrium points. And these are very special points. So here's the setup. Blue, this is the orbit of Earth around the sun. Now, if you put, say, a satellite right here at L1, no matter what time of year it is, the orientation of sun, Earth, moon, the satellite will stay here. As the Earth orbits around the sun, this satellite is going to just stay right there, orbiting with the Earth, always facing the sun. So, in the example we say here, a wonderful thing to do is to put a satellite that's dedicated to studying the sun. This satellite that we put at Lagrange equilibrium point 1 is always facing the sun, and it's always in alignment with Earth. No matter what time of the year it is, no matter if it's January or March or September, doesn't matter. I can always draw a line going from the sun, it will cross L1 and intersect with Earth. So these are very special points, and they apply for all these other Lagrangian points. We could technically put a satellite at L5, and no matter where Earth is around the orbit, relative to the sun and Earth, L5, there'll still be a satellite there. And this is just due to the dynamics of the 3 bodies twisting and pulling on each other.